So today is officially the beginning of the geometry week on my channel. What this means is that every day from Monday, which is today, up until Friday, I will post one geometry related video, or two if the video is a little bit long. And to start off this week, I thought that I might present to you guys a proof that I, and possibly others without my knowledge, came up with for the sine and cosine angle addition identities. And this proof will not contain anything like complex numbers or matrices or the like. Namely, we will only prove these identities using geometry and trigonometry. So, let's get started with the proof. First, I would like to take a look at the following geometric construction. So, we'll take a pair of parallel lines like this, which we will call L1 and L2. And now we will choose one point on L2, which we will call A, and 2 points on L1, which we will call B and C, such that they are both on the same side of A. So we let B go here and C go here. Good. And now we will connect A and B, and we'll also connect A and C like this, and then we will project B and C onto line 2. So we will project C onto here, and this point we will call this point E, and we'll do the same thing for this, and we'll call this point D. Good. And now we will call angle BAE alpha and angle CAE beta. So this means angle BAC will be alpha minus beta. Good. And now we will let AD have a length of 1, since 1 is a good number to work with in mathematics. Okay, so now using this 1, we will calculate all the other side lengths in this diagram. So first, the length of BD is exactly the tangent of alpha, since the tangent of alpha is BD over 1, which is simply BD. And this means that by the Pythagorean theorem and the fundamental theorem of trigonometry, AB will have a length of secant of alpha. And now, BCED is a rectangle, since these two are right angles, and since these two lines are parallel, these two will also be right angles, and a quadrilateral with 4 right angles is exactly a rectangle. So we know that BD is equal to the tangent of alpha, which means that CE, since it is a rectangle, will also be equal to the tangent of alpha. Great. So now we will find the length of DE. And to do that, I would like to take a look at the tangent of beta. So the tangent of beta is equal to the tangent of alpha over 1 plus DE. And now we will swap the tangent of beta and the tangent of and 1 plus DE, or in other words, we will multiply both sides by 1 plus DE over tangent of alpha, which will give us 1 plus DE is equal to tangent alpha over tangent beta minus 1. And it simply means that subtracting, why is the minus 1? And then we'll subtract 1 from both sides, so we will get that DE is equal to tangent alpha minus, and then we'll do a common denominator, tangent beta, we write that T all over the tangent of beta. So this length will be tangent of alpha minus tangent beta all over the tangent of beta. So now we can see that, since as we said earlier, BCED is a rectangle, that BC will be equal to DE, which will in turn be equal to the tangent of alpha minus the tangent of beta all over the tangent of alpha And then we will calculate the length of AC using the Pythagorean theorem. So we know that AE is equal to 1 plus DE, which is the tangent of alpha over tangent of beta. And we know that CE is equal to the tangent of alpha. So this means that AC will be the square root of AE squared, which is tangent squared of alpha over tangent squared of beta. I was about to write another alpha, plus the tangent squared of alpha. Good. And now we will factor out a tangent squared of alpha, so we will be left with tangent of alpha times. And then 1 over the tangent square of beta is simply cotangent square of beta. And then cotangent square of beta plus 1 is, by the fundamental theorem of trigonometry, cosecant beta, or 1 over the sine of beta. So this will be tangent alpha over the sine of beta, which means AC will have, this is a weird wiggly line, tangent of alpha over tangent of, over the sine of beta. Sorry. Sine of beta. Okay, and now we can only focus on triangle BAC. So, triangle BAC, I will draw it again over here. Like this. So this will be A, this will be B, and this will be C. And now, as we have seen earlier, AB will have a length equal to the secant of alpha. BC will have a length equal to the tangent of alpha minus tangent of beta all over the tangent of beta. I wrote alpha was supposed to be beta, so tangent alpha minus tangent beta all over tangent beta, and AC will have a length of tangent alpha over the sine of beta. And very importantly, angle BAC will have a length of alpha minus beta. Good. And now we have all the information needed to find the sine of alpha plus beta. So how can we do this? Well, first we will find the sine of alpha minus beta, and later we will plug in negative beta and see what we get. So to find the sine of alpha minus beta, I would like to compute the area of triangle ABC. So the area of BAC will be, okay, so one way to calculate the area of a triangle is 1/2 times the product of two sides times the sine of the angle between them. So those two sides will be secant of alpha, will be AB and AC. So our area will be 1/2 times secant of alpha times tangent of beta over sine of beta times the sine of alpha minus beta. But then another way to calculate the area of a triangle is simply the base times the height. So we will be left with 1/2 times, and we'll choose our base to be BC, so this will be tangent alpha minus tangent of beta all over tangent beta. And then our height will exactly be the tangent of alpha, since by projection everything holds. So our height will be the tangent of alpha. And now we can cancel out the 1/2. We can cancel out the tangent of alpha. So we will be left with, and then writing everything in terms of sine and cosines, we will get 1 over cosine alpha times sine beta. So sine of alpha minus beta all over cosine beta times cosine alpha times sine beta. And this will be equal to, well, this thing right here, tangent alpha minus tangent beta all over tangent beta. So now we will expand this tangent alpha minus tangent beta over tangent beta by cosine alpha cosine beta over cosine alpha cosine beta. And now what this will do is we can rewrite tangent as sine over cosine, so sine alpha over cosine alpha. Here this will be sine beta over cosine beta, and the bottom will be sine beta over cosine of beta. And now in the denominator, the cosine of beta term will cancel out. We will be left with a denominator of sine beta times cosine of alpha. And there's a car going by, sorry for that. And for our first term, the cosine of alpha will cancel out, so we will be left with sine alpha times cosine of beta. And then for our second term, we'll be left with the cosine of beta will cancel out. So sine of beta times cosine of alpha. But then the two denominators are exactly the same, which means we can cancel them out. And we'll be left with sine of alpha minus beta is equal to this thing, namely sine alpha cosine beta minus sine beta cosine alpha. But then here we have sine of alpha minus beta, and what we want is sine of alpha plus beta. So what can we do? Well, we can just plug in negative beta instead of beta and see what we get. So we'll be left with sine of alpha minus beta, which is alpha plus beta. And here we will have sine alpha times the cosine of negative beta. But what is the cosine of negative beta? To do that, I would like to take a look at the unit circle. So we'll have our y-axis, our x-axis, and our circle. And then we'll choose a point on the unit circle and another point which is the reflection of that point above the x-axis. So our first point will make an angle of theta with the positive x-axis, and our second point will make an angle of negative theta. Okay, so now what will be the cosine of alpha? The cosine of theta, sorry. The cosine of negative theta. I'm getting lost in my words, it seems. So the cosine of negative theta is this length right here, which is exactly the cosine of theta. Therefore, cosine of negative theta is equal to cosine theta, which also proves that cosine is an even function. So we are left with a cosine of beta right here, and cosine of alpha times, and for the sine of beta, we can again take a look at our unit circle. So we know that this length right here is the sine of theta, which means this length right here will be the sine of negative theta. Therefore, the sine of negative theta is equal to minus the sine of theta. So minus sine theta, so minus will give us plus, and here we'll have a sine of beta, which is exactly the identity that we want right here. So our first identity is proved. And now I will clean up this board and we can start proving our second identity, namely the cosine angle addition identity. Okay, so now that I've cleaned up this board, we can finally start proving our second identity. And as we did similarly earlier, we will first find the cosine of alpha minus beta and get our expression for that. And then we will plug in negative beta instead of beta and see what we get. And what better way to find out what the cosine of alpha minus beta is than by using the law of cosine on this triangle. So, as I said, we will use the law of cosines. So, we will get that BC squared, or the tangent of alpha minus the tangent of beta, all over the tangent of beta squared. Oh, that exponent was a bit low. Will be equal to AB squared, or secant squared of alpha, plus AC squared, or tangent squared alpha, over sine squared beta, minus 2 times AB secant alpha times AC tangent alpha over sine beta times cosine of alpha minus beta. Okay, and now I would like to rewrite everything in terms of sines and cosines. So we will get, for our left hand side, as we did earlier by multiplying the numerator and denominator by cosine alpha times cosine of beta, this will give us sine alpha cosine beta minus cosine alpha sine beta all over cosine alpha sine beta. The whole thing squared, which is equal to secant squared alpha, which is 1 over cosine squared alpha, plus, and then tangent squared alpha is sine squared alpha over cosine squared alpha, so sine squared alpha over cosine squared alpha times, and then don't forget the sine squared beta, and then minus 2 times, okay, so our numerator will be 2 times tangent alpha, which is sine alpha over cosine alpha, so we'll have a sine alpha in the numerator, times our cosine of alpha minus beta, and our denominator will be, well, the secant of alpha is simply 1 over the cosine of alpha, so cosine of alpha, but then, because of our tangent alpha, which is equal to sine alpha over cosine alpha, we have an additional cosine squared cosine alpha, so we will be left with cosine squared alpha, and don't forget the sine of beta. Good. And now I would like to expand this left hand side, so we will get that this is equal to, write that equals a little bit, good. This will be equal to sine squared alpha cosine squared beta minus cosine plus cosine squared alpha sine squared beta minus 2 sine alpha cosine beta cosine alpha sine beta all over the denominator squared, which is cosine squared alpha over sine squared beta. Now this is a pretty big expression, but here is how we can simplify it. First of all, we have a cosine of alpha in the denominator everywhere, which means we can get rid of it like this. So now we can multiply both sides by the sine square of beta. So this will go out, and then sine square beta over sine beta is simply sine beta. So here we will have a sine of beta, and here the sine squared beta will cancel out, and here 1 times sine squared beta is simply sine squared beta. So now we have sine squared beta plus sine squared alpha minus 2 sine alpha cosine alpha minus beta sine beta is equal to sine squared alpha cosine squared beta plus cosine squared alpha sine squared beta minus 2 sine alpha cosine beta cosine alpha sine beta. Okay, and now I would like to multiply everybody by -1, or in other words, negate both sides. So minus, minus, plus, minus, minus, plus. And now I would like to add sine squared alpha plus sine squared beta to both sides. So this will die, and here we will have plus sine squared alpha and plus sine squared beta. Now why do I do this? Well, for these two terms, we will have factoring out of sine squared alpha times 1 minus cosine squared beta, on which we can use the fundamental theorem of trigonometry to get that this is equal to sine squared alpha cosine squared beta, sine squared alpha sine squared beta, sorry. And similarly, on these two terms, we can factor out a sine squared beta, so sine squared beta times 1 minus cosine squared alpha. And again, we can use the fundamental theorem of trigonometry to get that this is equal to sine squared beta. This thing is equal to sine squared beta times sine squared alpha. But then, these two terms are exactly the same, so we can combine them. So our expression will become 2 times sine squared alpha times sine squared beta, 2 sine squared alpha sine squared beta, plus this thing right here, 2 sine alpha cosine beta cosine alpha sine beta, 2 sine alpha cosine beta cosine alpha sine beta. I barely have space. And this will be equal to what's left here, namely 2 sine alpha sine beta cosine alpha minus beta. We just swap these two terms because multiplication is commutative. And now we can divide both sides by 2 sine squared alpha sine 2 sine beta alpha sine beta. So this will die, the 2 will die, and the exponents and sine squared alpha sine squared beta over sine alpha sine beta is simply sine alpha sine beta. Therefore, we have that cosine of alpha minus beta is equal to, let me see, cosine alpha. The sine alpha, I can solve the wrong thing. So cosine alpha cosine beta minus, it's a plus sine alpha sine beta. But now we have cosine of alpha minus beta, and you want cosine of alpha plus beta. So as we did earlier, we can just plug in negative beta instead of beta and see what we get. So cosine of alpha minus beta, which is plus beta, is equal to cosine alpha times. Okay, and now from this diagram, as we saw earlier, cosine of negative beta is simply cosine beta, so cosine beta, and then plus sine alpha times, and from this diagram again, as we found out earlier, sine of negative beta is equal to negative sine beta, so the plus will turn into a minus, and we'll be left with a sine beta over here. And this is exactly the identity that we want, and hence we have proved this identity and both identities. And now I would like to leave it as an exercise to the viewer to use what we found here to determine to express tangent of alpha plus beta in terms of tangent of alpha, in terms of tangent of beta, or in other words, derive the tangent angle addition identity. So this has been a video. Thank you guys for watching. I'll see you in the next video. Bye.